Okay, so now let's look at another example of a situation where we can calculate limits by looking at the graph of a function. So we've got our piecewise function, g, defined by the following rule. So g of x is equal to x squared if x is not equal to 0, but in the case where x is equal to 0, then g of x outputs 3. So that's our piecewise function, and we're asked to find these three limits. So remember, these two limits are called the one-sided limits, and the limit that we see here is called a two-sided limit because the direction is not specified. Okay, so how are we going to do this? Well, let's start by drawing a sketch. And it helps that g is almost the standard upward-facing parabola centered at the origin. The only difference is its behavior at the point x equals 0. So if we were to do a sketch of the graph of this function, we're almost going to get that parabola, but we're going to have a hole at the vertex, or sorry, a hole at the vertex, which is going to be at the origin. So go up like that. And then, well, what happens at the point x equals 0? Well, that's where this special rule kicks in, right? G of 0 is equal to 3. So right at the point 3 on the y-axis, there's going to be a point on the graph. So that's the graph of your function. Now, what about these limits? Well, let's start with the first one. The limit as x approaches 0 from the left of g of x, that's what we're calculating. So what's that going to be? Well, start with this piece where it says x approaches 0 from the left. So go to the x-axis, put your pen on the x-axis, and trace the path towards 0 from the left. And then ask yourself, well, what is the corresponding path along the curve? And that's this path here. And then finally you'll say, okay, well, this corresponding path along the curve, is it approaching a point in R2? And the answer is yes, it's approaching the origin. Now, the origin isn't a point on the graph itself, but that's okay. Remember, the limit notation doesn't care what happens. I should point over here. This limit does not care what happens at x equals 0. It only cares what happens as x gets close to 0 from the left. So when you're tracing this path along the curve, you're only ever going to get close to that point. You're never going to actually touch it. So as far as the limit's concerned, it has no idea whether this point is a point on the actual graph of the function or not. It doesn't matter. It's completely irrelevant. So we are approaching the origin. Finally, you're going to ask the question, what's the y-coordinate of the point you're approaching? And the y-coordinate of the origin is 0, so this is going to be 0 as well. Let's run through the same line of logic again, going from the other side. The limit as x approaches 0 now from the right of g of x. Okay, so start down here. Approach 0 from the right along the x-axis. So you're going to approach 0 from the right, and then you're going to stop and ask yourself, okay, what is the corresponding path along the graph? And that is this path up here. We would be coming down towards the origin again, like this. So the answer to the question, does this path approach a point in R2? And again, the answer is yes, it's the origin. So then you ask yourself, okay, if it is approaching a point, what is the y-coordinate of that point? And again, since it's the origin, the y-coordinate is 0. So that's our two one-sided limits. Now, for the two-sided limit, if you've already calculated both of the one-sided limits, calculating your two-sided limit is easy. It's going to be one of two things. Either these two limits were equal to the same value or they weren't. And in this case, they were, right? They were both 0. So in this case, when they do equal and they are equal to some common value, or that the two one-sided limits agree, that's another way of saying it, well, then your two-sided limit is just going to be equal to that same value as well. But if these two values were different, or if one of them just was not calculable, we'll see examples like that soon. But for now, just think of it this way. If these two one-sided limits disagree or are different values, well, then the two-sided limit is said to not exist, right? So since they are equal, since the limit as x approaches 0 from the left of g of x is equal to the limit as x approaches 0 from the right of g of x, and both of those limits were equal to 0, we conclude that the limit as x approaches 0 of g of x is equal to 0. And that's the best way to finish it off. So we found all three limits. Okay, so if you have the graph, it's straightforward. Let's do another example where we have a graph. And this is an example where we aren't actually given any information about the function directly. We're only just told what its graph is. So we actually don't know what rule exactly is defining this function f, but we are given its graph, and it turns out that that's going to be enough. So, and we want to find all 6 of these limits. So let's start with part A, and we can knock all 6 of these off. So let's start with part A. The limit as x approaches -2 from the left of f of x. Let's work that one out. Okay, so start with this part. X is approaching -2 from the left. So you're coming in along the x-axis and you're coming towards, how about I extend this just so it's a little bit easier to point to. So we're on the x-axis and we head towards -2 from the left. So we're coming in this way. Ask yourself, what's the corresponding path on the graph? And that would be this path up here. And it's approaching a point. It's approaching this point up here. So then you're going to say that this limit is whatever the y-coordinate of this point is. And since that y-coordinate looks like it's 3, we're going to say that this limit is 3. Okay, let's do part B, which is the limit as x approaches -2 from the right of f of x. So we're doing this one up here. Okay, so now x is approaching -2 from the right. So do the same thing on the x-axis, but just come in from the other direction. You're approaching -2 from this direction. The corresponding path along the curve would be this path here. Is that approaching a point? Certainly it is. It's approaching this point. And what's the y-coordinate of this point? Well, it's equal to 1. So that means this limit is actually 1. Now, in both of these cases, it's worth pausing for a moment and making note of the fact that in both of these calculations or limits that we worked out, we didn't care that this point was solid and that this point was open. If you were to reverse it, if I were to shade in this point and make it solid and then erase this one and make it open, it wouldn't change anything here. Because, again, the limit does not care what happens when x is equal to -2. It only cares what happens when you get close. So these one-sided limits don't depend on the fact that this dot was solid and this dot was open. I want that to make that as clear as I can. Part C is the two-sided limit as x approaches -2. So the limit as x approaches -2 of f of x is equal to, well, what did we say before? We said if the two one-sided limits are the same, then whatever the common value is what you would put here. But these aren't the same, right? One is 3 and then the other one is +1. So they aren't actually the same. So this limit does not exist. And I caught myself doing it again. I wrote the equals before I knew what I was actually going to put down. But if you're going to say do not exist, I mean, you can write the limit as x approaches -2 of f of x equals does not exist. If you write that, that's totally fine. But I want to get rid of it and just write dne. Just so it sounds like an actual sentence. Okay, so that's, you'll forgive me, I hope, for scratching that out. So that's part C. Let's do part D now. So we've got the limit as x approaches 3 from the left of f of x. So start down here as usual. Approach the point 3 from the left along the x-axis. Now go up and trace the corresponding path along the graph. It looks like you're getting closer and closer to this point. So what's the y-coordinate of this point? Well, maybe you don't know for sure, but it certainly looks like it's whatever the y-coordinate is here, and it looks like it's about halfway up, right? So let's say 2. Let's say that this y-coordinate, this notch on the y-axis is equal to 2, and that would mean that the y-coordinate of this point is 2. So we can say that this is equal to 2. For part E, the limit as x approaches 3 from the right of f of x. What are we going to do from the right? So x approaches 3 from the right, go this way, and then trace the corresponding point along the curve, and you get here. You get to this point. Well, what's the y-coordinate? Well, same thing. It's the y-coordinate is 2. We just said that. So this will be 2. And then since these two one-sided limits agree, when we go to do the two-sided limit in part F, it's going to be whatever this common value is. Because if these two agree and are within whatever their common value is what the two-sided limit will be. So for part F, we can say that the limit as x approaches 3 of f of x is 2. And so that's how you can use the graph to evaluate limits. And again, it's worth noting that if I shaded this point in and made it solid, it wouldn't change anything. All these limits would be the same because we don't care what happens at the point x equals 3. You just care what happens as you get close from either direction. Okay, so that's the end of that page. We'll talk a little bit more about limits in one more video, and then that'll end off this section.